In this video, we are going to discuss the fundamental theorem of calculus. Our learning objectives are fairly straightforward. Use the fundamental theorem of calculus to take the derivative of an integral, although that's a bit sloppy way of saying it. And we'll also want to use the fundamental theorem of calculus to evaluate integrals. Since our topic is the fundamental theorem of calculus, I do want to point out something. If you've got something that has the name fundamental in it, that should be a pretty huge clue that it's really, really, really important. And this is not an exception. The fundamental theorem of calculus is like, by the way, what's the derivative? I mean, how important is it to know what the derivative is? How important is it to know what the fundamental theorem of calculus is? Massively, massively important, because it's a pretty remarkable connection that ties differential calculus, where you take derivatives, together with integral calculus, where you're doing integration. Before we can start looking at exactly what the fundamental theorem of calculus is and what it says and how it works, we kind of need a little bit of a reason. Okay, here's where we started doing an investigation. So, what does this mean? What does an integral mean? We remember that this symbol has an interpretation of area underneath a curve. Specifically, we are looking at the curve t squared. Okay, so let's start by graphing that. T squared looks, dang it, too high. If we're looking at it, we've got this general type of shape for our parabola. And we're looking at between the vertical line of x equals 2, so 0, 1, 2, 3, 4. That's a 1. Here's 2. From 2 up to 4, and underneath the curve between the x-axis. This region, this notation is just saying what is the area underneath this particular curve. That's all. Well, this is a piece that I need to copy and then put it on our next page, because looking at it, how is this different than what we were just seeing? On this one, you correctly noted, we're not going up to a 4. We're talking about the area from 2 up to some number. And we don't know what it is. This is where our variable's coming from. We're still examining area underneath a curve, but it might be that we're examining the area underneath the curve from 2 to 2.1. Maybe it's up to 3. Maybe it's the area up to 4, or maybe way higher with the area of 5 or 6 or 10 million or whatever, but that's a variable. In any case, we're still investigating this piece of what is the area underneath t squared between 2 and some rightward bound. Well, we can actually define a function based on this. We could define the function saying, what is the area underneath a graph between 2 bounds? As just a general quick sketch, we could be saying, here is the graph of my function f of t, and we could have the picture itself. This function g is saying, from some number a over to some number x, and we don't know what x would be. Okay, get that back. Over to some number x. What is the area underneath the curve, between the curve and the x-axis, and in between these two lines? Of course, as we move the x over and around, we're going to wind up changing a lot of the area. But this is a function. We could create functions about area. This is where we could start doing a little bit of an investigation. G of x is this type of function. It is the area underneath the curve from this graph f that's shown, and it's the area starting at 0 and going over to some number x. So, what is g of 0? That's asking us what is the area starting at x equals 0 and ending at x equals 0. Yeah, what's the area of something with 0 width? Nothing. What about the area between 0 and 1? Where is that region? Where is that region? Well, we're going in between 0, underneath the graph, over to 1, and so we're saying, what is that area? Well, we can visually see 1.5, so we get 1.5. What about the area from 0 to 2? Well, that's just saying go over to 2 then, and what's the area of that? Total of 2. And of course, we could use just a quick area of a triangle formula. We could count it knowing that we have exact half for the slope on that. Okay, what about then the area from 0 to 3? Okay, so then we're saying add on that part, so we get 2.5. The area up to 4. Okay, combined together, 2 and 2, that would give us an area of 4. And g of 5 then, g of 5 adds on another 2.5 in the area, giving us 6.5. G of 6. G of 6 is going to add on this region, which adds on another 3.5, which gives us an area of 10. And so all of this huge piece is what we're seeing for the area in A. Okay, this whole block of stuff, as I was just saying, that is part A. Part B then says estimate G of 7. Remember, G of 7 is saying the total area from 0 up to x being 7. We're not saying what's the height of 7. We're saying the total area underneath the curve. So we know these pieces that we've already done just by using area of triangles, we know that it's a total of 10. G of 7 then is going to say add on this much more. So estimate how much area does that look like. Okay, I'm looking at this and saying that's really close to 1. This looks really close to 1 when you combine those two pieces. That's, what, 2.75? I mean, it's an estimate, so it doesn't have to be perfect. But just looking at it to me, that looks like it's about 2.75. So I'm going to say my estimate for part B, it's about 12.75. The 10 we already had, combined with the additional about 2.75, about 3, as an estimate for it. Okay, so let's consider this now. Looking at part C, does G have a minimum value? Yeah. Does it have a maximum value? Well, it depends on kind of where the graph goes from here. When we're looking at this particular graph, when we look at this particular graph, the entire domain seems to be listed within just this window of 0 to 7. So does it have a minimum value? Yeah, the minimum value of this one was an area of 0. Does it have a maximum value? Yeah, the total area of the entire piece would be a maximum value. Now, we don't know exactly what it is. Our estimate of the maximum value was 12.75. Now, could we sketch a rough graph of G? Yeah, well, we have a crap load of points. Having so many points, we should be able to just plot the points and connect the dots to finish it off. Would you like to take the time to do that, or you're okay with just plotting points and connecting dots? Okay, class has told me we don't need to take the time, so that's one piece that you'll know what you would need to do. Just plot some points. One of the things that we're going to then look at is we have this function now. We have this function that says, what is the area starting at some leftward bound and going up to some right bound that's our variable. We have this new type of function, which I'm sure you've never worked with before. What is the derivative of this function? What is the rate of change in this particular function? Now, we know that we could go through and kind of create this quick little sketch where I was going to say, it's going to leave it for you guys, but just quick. 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 0, 0, 1, 2, 3, 4, 5, 6, 7. 1, 1.5. 2, 2. 2, 2.5, or 3, 2.5. 4 goes to 4. Then 5 goes to 6.5. Then we had 6 goes all the way up to 10. Then we had it going up to there. And so we could kind of connect the dots to create a sketch of our graph. And we could look at it and say, with this sketch, what is the derivative? What is the derivative? What is the derivative? What is the derivative? And we can get each of our slopes of the tangent lines, and we could kind of create a sketch. This is where the fundamental theorem of calculus comes into play. Rather than having to create the graph and then go through and start drawing in all these pieces, the fundamental theorem of calculus gives us this incredibly awesome shortcut. If you define the function as we just did, the area underneath a curve starting at a left bound and going up to a variable right bound, as long as we define the variable this way, here are a couple things that we know are cool. Number one, this function g is a continuous function, since we're talking about area. As long as we have a continuous beginning function, the area function will be continuous. Moreover, the area function g is differentiable also on the open interval. But here's the coolest part about it all. The derivative of this area function is just this thing itself. That is telling us that if you take the derivative of this function it's just f of t. And this is an incredible shortcut, and the proof of it is really cool, though we don't have the time to go over it today. But basically, you know how you wind up with this piece that where you say squares and square roots get rid of each other? And then you've had the pieces that multiplying and dividing are inverses, they can get rid of each other. The fundamental theorem of calculus is really a proof that says derivatives and integrals are inverses. They cancel each other out. So derivative compared with integral in this particular format wind up with just our function f of x, which is an incredible shortcut. It's not something that should have been guaranteed to be true, but the fact that it is true makes it incredible. Remember our work where we were doing antiderivatives before? with our previous work? Well, if you want to take the derivative of an antiderivative, you get back where you started, which intuitively seems like it should make sense, but the fact that it is actually true, that's why it's the fundamental theorem, because it's massively, massively important for pieces like this. Sketch the area represented by g of x equals the integral from 1 to x underneath t squared. So, what does this look like? Sketch the area. Well, we'll have to start with our graph of t squared. Okay, this is t squared coming from right here. And we want the area from 1, okay, at x equals 1, over to the bound of x, understanding, of course, that this is a piece that could change. And so this region is our function. The area of that region is the output for our function. And this is going to be any particular x value. We don't know if it's x equals 2 or 4 or 10 or whatever. It's just some right bound x. Now that we have this part, let me erase. Now that we know we have g of x equals this, what is g prime of x? Not t squared, x squared. We do wind up having the change of variables. But there we go, we're done. We have our derivative. One of the pieces that we're going to tie into upcoming, well, if this is the derivative, what is the antiderivative of g? Is there another way to rewrite this particular thing using a function that looks a lot like x squared? That's going to be the second part of the fundamental theorem of calculus coming up. It's going to tie in area with antiderivatives with derivatives. Okay, sketch the area represented by the function g of s as g of s equals the integral of t minus t squared all to the 8th power from 1 to 8. Okay, so first things first. Sketch the area is saying we need the graph of t minus t squared all to the 8th. How do you want to get the graph? I'm assuming people are going to vote, hey, let's plug this into the calculator and get the picture. Fine. We can use our graphing calculators to get the picture for what t minus t squared all to the 8th looks like. If you're not going to use the graphing calculator, we know that we could use the first derivative test to get some minimums and maximums. We could get the y-intercepts. We could go through all our graphing techniques that we were developing in our last unit to create the picture. But ultimately, in an effort of saving time today, let's just type in t minus t squared all to the 8th into our calculator, which we're noting then here is a quick sketch. So when we're looking at it, it looks like it's incredibly, incredibly flat, but coming back to our piece, we wind up with, here is a rough sketch of what it looks like. We'd have 1, -1. And so the area underneath the curve from 1 to x, we're looking at the area underneath this particular part. Understanding that this is a piece that is rising rapidly, rapidly, rapidly. And so if we were to zoom out or zoom in, we would be able to look at this in a different viewpoint. If we were to zoom out a lot, we could actually change the way we look at it, but the idea is still the same. What is the area underneath this particular curve? Now, given that we have g of s, what is g prime of s? S minus s squared to the 8th. And we're done. That's a very, very quick way to be able to get the or to be able to get this derivative. Fundamental Theorem of Calculus. It has the name fundamental for a reason. It's massively important. And it provides some incredible shortcuts to be able to do certain things very, very quickly. Okay, what about this one? H of x equals the integral from 2 to 1 over x sine of t to the fourth. Well, once again, we've got to be able to say sine of t to the fourth. We could type that into our calculator. And let's go and say, come on, just delete. So we've got the sine of x to the fourth power. And there's our graph. And so when we're looking at this particular piece, we would have hang on, I'm starting that in a weird spot. I want to make sure that I'm getting an accurate sketch. So it's kind of flattened out, comes up, flattens out, and that's got to go down. Nope, because it's to the fourth power, these are all positive. Okay. And so my sketch is a bit crappy, but we'll get the idea anyhow. We want to know the area bounded between 1, I'm sorry, not 1, we had 2. So coming back here, we can just say, I'm sorry, that's x equals 2. Blah. So looking, we're saying the area from about here over. Here's one of the things that we're going to be a bit precarious about. If we plug in x equals 2, if we want to know h of 2, this is talking about the area between 2 and not 2, but 1 over 2. So we're looking at this type of area. And if we're plugging in x equals 5, then we're saying the area from 1/5 over. And if we're plugging in negative, or if we plug in h of 1/3, 1 over 1/3 is going to be 3, so that's giving us the area from 2 over to 3. So we can have the rough sketch of the area, but ultimately what we're trying to do is say, let's use the fundamental theorem of calculus to get the derivative. Most students are just going to say, well, hooray, we've got sine of t to the fourth, or sine of x to the fourth. This is wrong. Why? The big issue that you have to be careful about here is paying attention to this upper bound. The fundamental theorem of calculus tells us that we can take this quick little shortcut as long as we have bounds that are going from a constant number a up to x. This is not 1 over x. It's not x squared or cosine of x. It must be a plain x. Otherwise, this does not work. So our challenge then becomes, since we have 1 over x, how do we make it work? In order to do that, we're going to wind up using a change of variables. We're going to say, let the number u be equal to 1 over x. Okay, so if u is equal to 1 over x, we will note then, if we are saying u is 1 over x, we could then take the derivative of u, du dx. That's going to be negative 1 times x to the negative 2, which we're noting is just negative 1 over x squared. This is going to play a role for us. because remember what we're trying to do. H prime of x is taking the derivative of this piece. But since the fundamental theorem of calculus only works if this is a variable and not a function of some other variable, we're taking it and trying to make a change so that we're going from, okay, we're going to note this is going from a 2. If x is equal to 2, then u is going to be 1 over 2. So we're changing the lower bound from being a 2 in x over to be a 1/2 in the u variable. Still not going to be a problem because the fundamental theorem of calculus requires that we have a constant at the bottom, and we have a constant, so we're okay. But then 1 over x we've changed to a u. Do you notice how these bounds are now fitting what we had required from the fundamental theorem of calculus? We're going from a variable, or from a constant, up to a variable. And we can still have our same sine of t to the 4th power dt. But we still have the same problem that we are taking this derivative with respect to x, even though we've got different pieces, even though we have a different variable. This is where the chain rule is coming into play. If we want to change it from the derivative with respect to x, it's going to be the derivative with respect to u multiplied by du dx. Remember kind of the sloppy algebraic shortcut that we were looking at was like d dx is like d du times du dx. How kind of the sloppy shortcut was the du's wind up canceling and you wind up with just d dx. That's the idea behind what we're doing here. And so by setting up the change rule, by using this change of variable, we can now say fundamental theorem of calculus kicks in right here. That stuff's gone. And we wind up with the sine of u to the 4th times du dx. But now we can do the change of variables back from being a u into the x. U was 1 over x. Du dx was -1 over x squared. And we have our answer. This is the derivative. A little bit harder, right? This technique of applying a change of variables is something that for some people are going to be new, it's going to be a bit challenging, but it is an incredibly common technique in calculus. If you have pieces that don't fit your theorems, change the variable into something that does fit the theorem, do the work there, and then convert it back into your original variables. It's incredibly common. We will do it a lot moving forward. All right, so backtracking this a little bit. The fundamental theorem of calculus has a second part to it, and it is used to address problems more like what we had back at the beginning, where when we were looking at this and we said, what is the area underneath the curve between 2 and 4? Well, part 1 is used to address what is the derivative if you're going up to a variable x. Part 2 is actually used right here. What is the area underneath the curve? Essentially, how do you evaluate this particular type of function? If we were defining g of x equals this piece going up to x, how do you evaluate the function, not the derivative, but the function itself, g of 4? How do you get the area? The fundamental theorem of calculus, part 2, gives us the answer. Whoa, where is it? Here we go. And here's the short version. Remember when we were doing our antiderivatives? That's where it's going to come from. If you want to take the integral and get the area from a left bound of A to a right bound of B, and what is the area underneath that curve, we are going to have to start by getting the antiderivative of the function. That's why we're going to use a capital F for antiderivative of lowercase f, so we know that there's a connection between them. Once you get the antiderivative, any antiderivative, evaluate it at the upper bound, evaluate the derivative, or evaluate the antiderivative at the lower bound, and you subtract the two. That's it. So in order to do it, we're looking at pieces like this. What is the area underneath sine of 0 between pi over 6 and pi? And we're not going to create this sketch this time, but just what's the area? Well, this tells us what is the antiderivative of sine. What function will give you the derivative sine? Well, cosine has derivative negative sine. So our antiderivative is negative cosine of theta plus a constant. But we know this could be any constant by the fundamental theorem of calculus, so why not just say, let's use a constant of 0? Because if it's a constant of 0, then we're not going to bother writing it. Well, this is our term, and we now have to evaluate it. This is a term that tells you evaluate from pi over 6 up to pi. This vertical line is a notation that says evaluate, plug in pi, then subtract off what you've got from plugging in pi over 6. So it tells us negative cosine of pi, subtract the negative cosine of pi over 6. Well, of course, subtracting the negative is saying plus the cosine of pi over 6. So, what is the cosine of pi? If you don't instantly remember, draw your unit circle. Pi radians is right here. What's the cosine? Negative 1. So we would get the opposite of negative 1 plus the cosine of pi over 6. Pi over 6 we know is a 30-degree angle, so we're saying based on having a 30-degree angle with 30, 60, 90, what is the cosine? Cosine is adjacent over hypotenuse, so we can say adjacent is, okay, if we're not using unit circle, we had 1, 2, square root of 3. So we'd have the square root of 3 over 2. And therefore, our total answer is 1 plus the square root of 3 over 2. And we've got an answer. Every time you want to evaluate, this is called a definite integral. When you have two constants for the bounds, it's called definite. If you evaluate a definite integral, you're going to first take the antiderivative, evaluate the antiderivative at the upper and lower bounds, and then just subtract the two. And our last problem then, what's wrong with this? Okay. Well, we're going to note, if we want to get the area underneath the curve 4 over x cubed between negative 1 and 4, we're looking at it and saying we want to have this particular piece saying, here's our answer. Well, you'll note one of the things that they did is they just went through and quickly took the antiderivative of 4 over x cubed to get this antiderivative. And you'll note if you take the derivative of negative 2 over x squared, you do wind up with negative 4x to the negative 3, which is negative 4 over x to the third. So they did, wait, 2, -4. There we go. Okay, let me, and so we can see one thing that potentially that went wrong with it. When we're looking at this particular thing, we had a negative get thrown off. This antiderivative should have been a positive 2, not a negative 2. There is another issue at play here, and one that we are going to spend some upcoming time learning how to fix this potential problem. Please notice that this is going from -1 up to 2. -1 to 2 includes a 0. You cannot plug in a 0 to that denominator. At x equals 0, this function is discontinuous. One of the rules behind using the fundamental theorem of calculus, this function must be continuous. If you have a hole, if you have a gap, if you have a jump, if you have any type of discontinuity, like we just experienced with having that vertical asymptote occurring at 0, this does not work. At least you can't trust it, and so that's an additional problem. One of the reasons why we're running into some pieces is they were using the fundamental theorem of calculus part 2 when they were not allowed having a point of discontinuity in the closed interval from -1 to 2. That is a very serious problem, and instantly at that point we could have thrown out all of their work because it doesn't apply. There are other ways to get around that. There are ways to fix this potential problem, and those are some of the things that we are going to be studying upcoming. Learning ways to fix potential problems like that. Let's go back to our learning objectives and just quick do a recap. Can you use the fundamental theorem of calculus part 1 to take the derivative of an integral type function? Additionally, can you use the fundamental theorem of calculus part 2 to evaluate a definite integral? If you can use part 1 and part 2 of the fundamental theorem of calculus, which you can see why they typically abbreviate it FTC, then you're all set and you've met their objectives.